determinant of k times a equals k times the determinant of a for any real number k. False. Yeah. So the theorem that was given in the book said that if you do, if you multiply a single row by a scalar, that changes the determinant by a factor of that scalar. So, but k times a means multiply every entry in every row by k. So it's actually going to be something other than k that goes here, and you're going to work through that in your activities actually. If A is a triangular matrix, then the determinant of A is the what of the entries on the main diagonal? Product. True or false, the determinant of A equals the determinant of A transpose? True. Good job. By theorem 2, if you have a triangular matrix, if you swap the rows and the columns to take A transpose, the diagonal entries will be the same. So then the determinant of A and A transpose would be the same too. Okay, so you took your test last class. It's not graded yet. I will for sure have them Thursday. Okay, so we're going to learn how to compute determinants of square matrices that are larger than 2 by 2. We have a handy little formula for 2 by 2 for the determinant. What is that? AD minus BC, right. So for larger matrices, the determinant is much more tedious to calculate. So we're going to learn actually both methods today, one in each lesson. And then after that, once you kind of get how to do it, you can, like on a quiz, I might ask you to write it all out. But if you need to calculate a determinant to answer some other kind of question, it's okay to use your calculator. In the math section of matrix, they have determinant as an option. So you can always use that to check your work of calculating also. Okay, so I want to calculate the determinant of this 3 by 3 matrix using a cofactor expansion across the first row. All right, so across the first row, or a cofactor expansion means you take the entries from the row or column specified, or of your choice, right? And you multiply each of those entries by the matrix that remains if you cross out the row and column of that entry. Okay, and then there's some stuff with alternating signs that we'll go through in A, and B does a different thing with the alternating signs. All right, so if we're going to go across the first row, that means take each entry from the first row, and you're going to multiply by the determinant of some 2 by 2 matrix. So you start with the first entry, which is a 1. And when you're using an odd row or column, you start with a positive first term. And then my next term is a 3, but I alternate signs, so I'm going to do minus 3 times some 2 by 2, and then plus 5 times some 2 by 2. And notice I'm drawing lines without the little top and bottom piece of the bracket. That is a new notation for determinant. So instead of writing determinant of a matrix, those lines mean the determinant. Okay, so for my 1 times a 2 by 2, the 2 by 2 I'm going to write in here is the one that remains when I cross out the column and the row that 1 is in. So the 2 by 2 that remains is 1, 1, 4, 2. And then I do the same thing for the 3. Cross out the row and column that the 3 lives in, and you're left with 2, 1, 3, 2. And then finally you do it again for the 5, and you're left with 2, 1, 3, 4. And then now I just have to calculate 2 by 2 determinants, which are easy, AD minus BC. Okay, so I have 1 times 2 minus 4 times 1 minus 3 times 2 minus 3 times 1 plus 5 times 2 times 4 minus 3 times 1. And that should come out to 20. All right, so there's nothing special about the first row. You can do a cofactor expansion across any row or any column. So I'm going to calculate the same determinant. So I already know the answer is 20. And I'm going to calculate the determinant going down the second column. So I'm going to use 3, 1, and 4 instead of 1, 3, and 5 as my factors. But because I'm using an even numbered column, I start with a negative. Okay, so with A, I had a 1, I started with plus, and then I went minus, and then plus. When you start with an even, when you're using an even row or an even column, start with a negative. So I'm going to start with negative 3 times some 2 by 2, plus 1 times some 2 by 2 determinant, minus 4 times some 2 by 2 determinant. And then I go through and figure out what those 2 by 2s are. So for the 3, cross out the 3 row and column, and I'm left with 2, 1, 3, 2. And then for the 1, cross out its row and column, and we've got 1, 5, 3, 2. And then for the 4, cross out its row and column, and I have 1, 5, 2, 1. So I have negative 3 times 2 times 2 minus 3 times 1, plus 1 times 1 times 2 minus 5 times 3, minus 4 times 1 times 1 minus 5 times 2, and that should come out to 20. So this is just an algorithm. It's developed from the fact that when you're trying to find an inverse, you put the matrix on the left and the identity on the right, and you row reduce. So certain pieces have to be non-zero in order to make sure the identity appears on the left when you've row reduced. So this is just derived from that process, and I won't go through the derivation. So cofactor expansion can be tedious, especially if you're dealing with larger than a 3 by 3. When it's 3 by 3, it reduces to a problem that has 2 by 2s, which are easy. When you have a 4 by 4, it can be much more tedious. So you want to choose a row or column strategically that has a lot of zeros in it, because then there's a lot of stuff you don't have to do. So what do you want to use? Which row or column? Column 4? Sure. Column 4 or row 3 would be good choices here because they have a lot of zeros. So if I use column 4, then I'm going to have 0 times some 3 by 3 determinant. And I'm starting with positive. Nope, I'm starting with negative because it's an even numbered column. So I start with negative. And then I'm going to have plus 2 times some 3 by 3 determinant minus 0 times some determinant plus 0 times some determinant. All right, now, who cares, right? Because that's going to come out to some number. The determinant of a matrix is some number, but you're just going to multiply it by 0. So I'm not even going to bother figuring out what these are, let alone calculating those determinants. So I only have one 3 by 3 determinant to fill in here. It's the one that's left when I cross out the row and the column with the 2 in it. So I have negative 1, 0, 2, 0, 1, 0, and 0, 2, 2. All right. So I've got this 2 here. Copy that down. Now I have to find the determinant of a 3 by 3. To find the determinant of that 3 by 3, I have to do a cofactor expansion across a row or a column. Which row or column would you like to use? Row 2. Or column 1. Yeah, row 2 or column 1. They both have 2 zeros in them. So we'll do row 2. Actually, no, let's do column 1 because now we'll do an odd. We get an even one to start with. All right, so if I do column 1, then I'm going to start with a positive, right? So it's positive -1, right? So you just write down a positive and then you copy the number and then the determinant of some 2 by 2. And then you have -0 times some determinant plus 0 times some determinant. And these are like whatever, because you're multiplying by 0, so who cares? All I need to know is what goes in here with the -1. And I have 1, 0, 2, 2. So this becomes 2 times -1 times AD minus PC. So this is 2 times -2, which is -4. Okay, so that's it for the lecture. I just have shown you how to calculate a determinant for matrices, square matrices larger than 2 by 2, using a cofactor expansion. The activities is going to walk you through some properties of determinants, and then we'll have a lecture on a more formal lecture on properties of determinants. So we can go ahead and start that.